So in this example, we're given a simple circuit here, and we're asked to calculate the value of the current source, where the current source is here. And you see that the magnitude of this is not defined. And so the other information that we're given is we know the voltage between Y and W. So between these two nodes here, if we put a voltmeter across there, we're measuring 3.25 volts. So they're wanting us to use nodal analysis and see if we can determine what the value of the current source is. So let's look at how this is done. So the first thing we notice is that the values of the resistances are a little bit obscure, so they're not whole numbers. So this being the case, I typically will convert those to conductances. Just makes things a little bit easier, which means we just take the reciprocal of those. And so then instead of dividing the voltage by the resistance, we multiply the voltage times the conductance to get the current in and out of those nodes. So if we were to do that, I'll just write them on here. If we take the reciprocal of 0.9953, that's going to be about 1.005. If we take the reciprocal of 0.612, that comes out to be about 1.49. Of course, 3 is easy. That's just going to be 0.33. 1.797, that's going to be 0.556. And then 2.2, that's going to be 0.455. So again, that's just taking the reciprocal of each of those numbers, so just 1 over, and that's where we come up with that. So now we need to go through node by node and calculate or derive equations for the current, all the current leaving in and out of the nodes, to come up with some system of equations. So we'll also go ahead and take this opportunity real quick to define voltages. So at node W, of course, we'll have VW. At node X, we'll have Vx. And at node Y, we'll have Vy. And so using this, let's see if we can come up with some nodal equations. So the first one we want to look at is node W. So node W, and maybe we can write that in there, right? And so let's look at the currents going in and out of there. So we're going to define current leaving the node as positive. So the first thing we see is our current source, and it's shown going into the node. So that would make it negative, assumed to be negative. So that'll be a minus I. All right, so that's the first branch. So now we come and look at this resistor here. And the current in that case is going to be plus. Remember, we're dealing with conductances now. So it's 1.005 times VW. And then as we move down or around, we have this resistor here. And so to characterize that current, we're going to say it's going to be plus 1.49 times the difference in the voltages. So that's VW minus Vx. And so that's all of the branches coming in or out of that node. So then we should be able to set that equal to 0. So now we move around and we will take Vx. So we'll designate that here. So this is X. And first thing we see is the green resistor. So let's go ahead and write the relationship for that. And so that's going to be 1.49, the conductance, times the difference in the voltages. So that's Vx minus Vw. Next, we can take this resistor here. That's just going to ground. So then that's just the conductance times the voltage. So that'll be 0.33 times Vx. And then finally, we will look at this guy here. And so that's going to be, again, the conductance, which is 0.556. Oops, wrong pen. 0.556 times the difference in the voltages, so that's Vy minus Vx. And so that's all the branches coming in and out of that node. So again, set that equal to 0. And so finally, we can look at node Y. And we'll just write it like that. And so at node Y, see there's only 2 branches. So the first one is the blue, already highlighted blue. So that's 0.556 times the difference in the voltages. So that's Vy minus Vx. And then finally, we have this guy here in the green. So again, that's just the conductance times, which is 455, times the voltage Vy. So only 2 branches on that node. And so again, set that equal to 0. And so those are 3 nodes, 3 equations. Of course, we have the one final relationship. We'll do that with the yellow here. And so what that's saying is the difference in the voltage in those 2 nodes is equal to 3.25. So if we were to write that out, that's just saying that VW minus Vy is equal to 3.25. All right, so this is our system of equations. So now if we multiply everything out and combine like terms, what we should have then, let's do that for each of these. So for this first one, we'll have 2.495 VW minus 1.49 Vx minus I, and that's all equal to 0. Same thing here. If we can multiply everything out and combine like terms, we will have a negative 1.49 VW. We will have 2.376 Vx and minus 0.556 Vy. That's equal to 0. Same thing here. Multiply through. Combine like terms. We will get a negative 0.556 times Vx plus 1.011 Vy. That's equal to 0. And then finally, this one really doesn't change. We have VW minus Vy is equal to 3.25. All right, so now we have our system of equations. So now what we want to do is put this in matrix form, because I mean there's different ways you can solve this, but the probably the common way to do it is use linear algebra and create matrices and just do a matrices operator. So if we do that, we see we've got VW, Vx, Vy, and I are our 4 variables that we're going to use. And so let's go ahead and create this then. So for our red, and then let's distinguish this here. So let's draw a line here. And now let's come back and say for the red equation, what we're going to have then is 2.495 minus 1.49, 0, and minus 1. And then for the purple, we're going to have minus 1.49, 2.376, minus 0.556, and 0. And again, this is VW, this is VX, this is VY, and this is I, just keeping up with what's going on here. So the next one is green, and that's going to be 0 minus 0.566, 1.011, 0. And then finally, for the yellow, that's easy enough. That's 1, 0, minus 1, and 0. So here's our coefficient matrix. And again, this is going to be times VW, VX, VY, and I. And then finally, this is going to be equal to the answers to each of these. So for the red, it's a 0. For the purple, it's a 0. For the green, it's a 0. And then for the yellow, it's 3.25. So now, again, using your scientific calculator, you should be able to just plug these in. And so when you do that, you would enter this array first and then divide it by this matrix, which most scientific calculators will just allow you to do that by punching things in. And when we do, what we come up with then is Vx is equal to 5.38 volts, Vx, let me rewrite this. I started off on the wrong variable. Sorry about that. So VW is equal to 5.38 volts. Vx is equal to 3.87 volts. Vy is equal to 2.12 volts. And I is equal to 7.65 amps. And this is what was asked for. What is the value of the current source? So there's the answer to that equation using nodal analysis using the information that was given.